Welcome back to Integration Techniques. We're up to Lesson 7, Partial Fractions. Integrating something like 2 over x take 4 plus 8 over 2x plus 7 dx can be completed using techniques previously studied. The solution: when I see 2 over x take 4, we think of natural logs. So that would be 2 ln x take 4. In this case, the 8 over 2x plus 7, the derivative of the 2x plus 7 is 2. So we're going to have 8 divided by 2, which is 4 ln 2x plus 7, plus our constant of integration. If you were asked to integrate the following expression, you might find it a little bit more difficult. So when I see this, we now have a linear numerator and a polynomial to the power of 2 as a denominator. How can we separate this? So how do you rewrite something like this into a simpler version, such as what we have here? We have two separate fractions that are a lot easier to integrate compared to our first. Rational expressions, in particular those with denominators that can be expressed with linear factors, can be transformed into partial fractions. These transformations are useful when the degree of the numerator is less than the degree of the denominator. Otherwise, long division is generally required before integration can be performed. Rational expression and its equivalent partial fraction. Here we have an expression such as fx over two linear factors. We can express that as an equivalent partial fraction, where we have a over ax plus b plus another fraction b over cx plus d. We might have another rational expression where we have a linear factor as a numerator and a quadratic factor expression as the denominator. Rewriting that as an equivalent partial fraction, we have two partial fractions that are a lot easier to integrate. We're going to explore that now. Example 37, integrate the following. The challenge in this question is to write the expression into two fractions. Let's start by rewriting this. Now 12x take 18 over the two linear factors here can be written as a over x take 4 plus b over 2x plus 7. Step 2, let's cross multiply to create common denominators. So we have our a times 2x plus 7, our b times x take 4, and we're going to multiply to create common denominators. The value of a can be calculated by equating the numerators. So this numerator has to be equivalent to this numerator. So 12x take 18 equals a outside of 2x plus 7 plus b outside of x take 4. Let x equal 4. If we let x equal 4, we're going to have b times 0, which means we can solve for a. So let x equal 4. We then started to simplify. We can now isolate and make a the subject, and a is 2. And we can finding b. The value of b can be calculated by completing the same process. Here we have our left-hand side, which is a numerator, and we're equating it with the partial fractions numerator. If we let x equal negative 7 on 2, when we sub in here, that's going to make a equal 0. Hence, we can find a value for b. So subbing in negative 7 on 2, I now rearrange, isolate b to make b the subject, and we have b equals 8. Now, expression can be written as partial fractions. So where I had an a and a b, they are now replaced with a 2 and an 8, and I've expressed the original integrand as partial fractions. The integral can now be easily evaluated. So the integral of 2 over x take 4 plus 8 over 2x plus 7 dx, as from the previous slides, is 2 natural log x take 4 plus 4 natural log 2x plus 7 plus c. So our job for this lesson is to change our integrand into partial fractions to then be able to integrate. This is an example of an expression that has a linear numerator being divided by a quadratic, which is a proper fraction. To show that, this integrand can be simplified or rewritten as partial fractions. That's our job. Let's rewrite our integrand, which is 5x take 4 over x squared take 6x plus 9. Something we should spot or observe with this denominator. We can rewrite it as x take 3 all squared. Now, applying our principles of partial fractions, that can be written as a over x take 3 plus b over x take 3 all squared. And to make these like denominators, let's multiply this first fraction by x take 3 over x take 3. Now we have a common denominator. Calculate A by equating numerators. So let's equate this with this. When we do that, we're going to let x equal 3. So now I've equated, there's my 5 times 3 take 4. There's my 5 times 3 take 4 equals A outside of 3 take 3 plus B. B equals 11. Now I've equated the numerators again, and we know that B is 11. So let's let x equal 0. Now we can find what A is. Rearranging and finding a value for A, we have A equals 5. Hence, we have shown that this can be rewritten as 5 over x take 3 plus 11 over x take 3 all squared. Let's now evaluate the integral. The first one will become a natural log, so 5 ln x take 3. And the second one, we can just apply the power rule. Here, if you remember, you'd have 11 would be written as 11 times x take 3 to the power of negative 2. If we add 1 to that, we get negative 1. Hence, that's why we have negative 11 over x take 3 to the power of 1 plus c. This is an example of an expression where the numerator and denominator are both quadratics. Here, my numerator is a quadratic and my denominator is a quadratic as well. We're going to show that this simplifies to this. Let's rewrite. Let's expand the denominator first. So x squared plus 3x take 4. How you make this 1 appear is by rewriting this as two fractions, or the sum of two fractions. Here we have x squared plus 3x take 4 over itself. That's the 1. Now this 11x plus 9 has now been rewritten. Have a look. I have an x squared and I have an x squared. I have a 3x and 11x, that's my 14x. I have a 19 and a negative 4, that's my 15. These two lines are still equivalent. I've just broken them up into two separate fractions. This becomes your 1, and I have 11x plus 19 over x plus 4, x take 1. So I've just factorized that again. And this can be separated into those two fractions by applying the processes followed in example 38 and 37. So now we have a over x take 4 plus b over x take 1. Multiply, cross multiply, so we create our new expression. Now equating our numerator to find a and b. So let's equate this with this. We can now let x equal negative 4 to find a, let x equal 1 to find b. First step, letting x equal negative 4, I now rearrange to find a, which is 5. Letting x equal 1, I now rearrange and find that b is 6. So all of this now, this can be rewritten here as 1 plus 6 over x take 1 plus 5 over x plus 4. Integrating this, the integral of 1 is plain old x. The next one is 6 natural log x take 1 plus 5 natural log x plus 4 plus our constant of integration. It looks tricky to start with, but following this process, you'll be able to break it down to partial fractions, and then the final integrand is far easier to anti-differentiate. In this example, a cubic expression is divided by a quadratic expression. We're going to follow a similar process that happened in example 39, just a slight difference. So the first step, I've created an x squared take 4x plus 4 over an x squared take 4x plus 4. They then will cancel out to leave with an x. Now, here I've written this fraction in green because that's what was created. So I think x times x squared is the x cubed. X times negative 4x is negative 4x squared. But I only had one x squared, which is why I made a 5x squared happen in my green fraction. X times 4 is 4x, but I really only had a negative 4x, so I better take off 8x. These can cancel out, so this cancels with this, leaving with x plus now a quadratic over a quadratic. Step 2. We now create the same quadratic again. So I might have my x squared take 4x plus 4 over x squared take 4x plus 4. They can cancel out to leave with the 5. Follow that process again. I had a 5x squared. I had a 5x squared, that's fine. 5 times negative 4x would be negative 20x, but I only had negative 8. So I better have 12 more of the x's. 5 times 4 is 20. I never had a 20, so I better take off 20. That cancels out with that. So I'm left with x plus 5 plus 12x take 20 over x take 2 squared. Next step. We can write this one as a linear over a quadratic, hence we can write it as a over x take 2 squared plus b over x take 2. Multiply the b over x take 2 by x take 2 over x take 2. Then I have a situation which I can create equating the numerators. We now have 12x take 20 equals a plus b outside of x take 2. We've equated the numerators. Let's let x equal 2. Letting x equal 2, we now have 24 take 20 equals a. We've now found a. To find b, let's let x equal 0. Letting x equal 0, we now have negative 20 equals 4 plus negative 2b. Rearranging, we can find that b equals 12. Hence, this initial integral we had can be rewritten as x plus 5 plus 4 over x take 2 to the power of 2 plus 12 over x take 2 dx. Let's anti-differentiate now. The x becomes the half x squared, 5 becomes the 5x. Using the power rule for integration, this will become negative 4 over x take 2. And lastly, will be a natural log, which will be 12 ln x take 2 plus our constant of integration. And that is a bit more challenging one. We have a cubic over a quadratic, but it turned out to be achievable by following a set of procedures. In this example, a cubic expression is divided by a quadratic expression. Polynomial long division will be applied. Our integrand is a cubic over a quadratic. So we're going to start polynomial long division by setting it up as follows. So I'm not going to spend too much time on our long division, but our x squared and the 3x cubed would be our 3x. And multiply your 3x by the x squared, by the 5x, by the 4. We have the following result. So this, subtract this, leaves us with this. So x squared and negative 17x squared would be negative 17. Follow that through by multiplying negative 17 by each of these. We're left with this. This, subtract this, is 74x plus 74. That's not going to divide into here. That's our remainder. So rewrite as partial fractions. Original integrand becomes 3x take 17, which was here, plus 74x plus 74 over x squared plus 5x plus 4. You could apply similar processes, procedures as you did in examples 37 and 38 to rewrite this as partial fractions, but we can do it a bit easier. This denominator can actually be factorized as x plus 4 times x plus 1, and I can factorize the numerator as being 74 outside of x plus 1. Let's cancel those factors. What we have is 3x take 17 plus 74 over x plus 4. Now we can integrate. The integral of 3x take 17 plus 74 over x plus 4 dx will become, using the power rule, 3x squared divided by 2, take 17x, that's a natural log, 74 ln x plus 4 plus c. That brings us to an end to partial fractions, lesson 7. Hope you found it enjoyable. Now go on and practice your questions by completing as many partial fractions exercises as possible.